Alright, now it seems that we're going. Alright. So today, yeah, it's been a week, so sorry about that, but well, not sorry, but I want to be looking at Rust a little more often than, taking a hiatus for a week and then coming back to it. But today we're going to look at generic types, traits, and lifetimes. So I'll just I'll read through this introduction and then we'll go from there, looking at these concepts in Rust. So every programming language has tools for effectively handling the duplication of concepts. In Rust, one such tool is generics. Generics are abstract stand-ins for concrete types or other properties. When we're writing code, we can express the behavior of generics or how they relate to other generics without knowing what will be in their place when compiling and running the code. Similar to the way a function takes parameters with unknown values to run the same code on multiple concrete values, functions can take parameters of some generic type instead of a concrete type, like 32-bit integer or string. In fact, we've already used generics in Chapter 6 with option t, Chapter 8 with vector t and hashmap kv, and Chapter 9 with result te. In this chapter, you'll explore how to define your own types, functions, and methods with generics. First, we'll review how to extract a function to reduce code duplication. Next, we'll use the same technique to make a generic function from two functions that differ only in their types of their parameters. We'll also explain how to use generic types in struct and enum definitions. Then you'll learn how to use traits to define behavior in a generic way. You can combine traits with generic types to constrain a generic type to only those types that have a particular behavior, as opposed to just any type. Finally, we'll discuss lifetimes, a variety of generics that give the compiler information about how references relate to each other. Lifetimes allow us to borrow values in many situations while still enabling the compiler to check that the references are valid. Alright, so now we'll learn about removing duplication by extracting a function. So before diving into the syntax, let's look how to remove duplication that doesn't involve generic types by extracting a function. And then we'll apply this technique to extract a generic function. This is to avoid code duplication. So alright, we'll look at this program. And we'll see how to extract a function out of this. Alright, so yeah, it says we got a variable number list. We place the first number in the list and a variable named largest, right? Largest is the first number in this list. Then it iterates through all the numbers in the list, and if the current number is greater than the number stored in largest, it replaces the number in that variable. So it's like a sorting algorithm. Or sorry, it's a maximum algorithm. So it's trying to find the maximum of this list of numbers. So it goes through each number in the list. If that number is larger than largest, then largest equals number. Of course, this takes in a vector with that has to be length greater than or equal to 1 in order to initialize largest. If we wanted to do it for two different lists, then we just duplicate it here, right? We have this list and this list that we want to get the largest of. But as it says, duplicating code is tedious and error prone. We would have to update the code in multiple places when we want to change it. So we're going to abstract away this duplication by creating a function that is going to be called largest. and it's going to take in a reference to a list of 32-bit integers, and it's going to return an integer, and it's going to do the same thing that it did before, where it takes the, so first of all, this gets automatically dereferenced because that tends to be what happens inside function arguments. That, I think, is the main place where automatic referencing and dereferencing takes place, is in the parameters here. And then you have your initialized largest to list. They don't check it because it's just an example. And then for every reference to an item in the list, for every dereferenced item in the list, if the item is greater than the largest, then largest is equal to that item. And then you can call this function on both of these vectors, both of these lists. Right, it doesn't accept a vector per se as the parameter. It accepts a slice. That's what the reference to list is. This is a slice, whereas this vector is it's a different type, but a vector can automatically be dereferenced into a sliced like this. That's something the compiler can handle. Alright, so this is not, they say, a dereference, but rather pattern matching, such that we destructure each I32 reference in the for loop so that item will pretty much be an I32 inside the loop body. So a little different than what I figured it was. Yeah, so this basic pattern was to identify duplicate code, extract the duplicate code into the body of the function, and then update the two instances of the duplicated code to call a function instead. And so after this, we're going to abstract away the types to use generics, such that this largest function will work on any sort of type, like a car. All right. So generics. We can use generics to create definitions for items like function signatures or structs, which we can then use with many different concrete data types. Let's first look at how to define functions, structs, enums, and methods using generics. Then we'll discuss how generics affect code performance. You know what? I should make this bigger so that y'all can see it better. I only just figured that. Like, all the rest of my streams were pretty small. Like, I sort of have to squint when I look at it, even from over here. I can't imagine you looking at it from a phone or something like that. Right, so here we're going to have two different versions of the largest function. One of them is for 32-bit integers, and one of them is for characters. And they both take in a slice of their respective types and return their type. But the logic is identical, right? In fact, even the syntax is identical. It's exactly the same. So it would be convenient to be able to use just a single largest function for both types. So that way, if you wish to change the logic of one, it's automatically applied to all types that it covers. Right. Even in a generic, we need to list the types that it accepts. Yeah, and so T is going to be the default choice. So now we're going to take in a T, and it's going to reference a slice of that T and return T. And this is so that the consumer of this function can specify what type is going to go into it. So this won't compile. If we try to compile it, let's see. If item is greater than largest. So consider a restricting type parameter T. I suppose the greater than operator is not defined for all types. Oh yeah, there it is. Binary operation greater cannot be applied to type T. And so we're going to restrict the type to those types which do have inequality operators defined for them. And for that, I suppose we have to implement partial order, which is a trait. Right, because we want to compare values of type T in the body, we can only use types whose values can be ordered. To enable comparisons, the standard library has the standard compare partial order trait that you can implement on types. You'll learn how to specify that a generic type has a particular trait in the traits as parameters section, but first, let's explore other ways of using generic type parameters. So that was to do it for functions, but I suppose in another subsection of the chapter, we'll learn how to actually implement the partial ordering trait such that this T generic takes those sort of types that can be ordered and thus restricts it. Well, restricts what the function can take as parameters, or rather arguments. Alright, so now we'll do a point. So this we're doing struct, and like it says, it shows how to define a generic point struct to hold x and y coordinate values of any type. So here we have a point where instead of what most would think of maybe like a 32-bit int, let's say, you define point as two successive 32-bit ints, but let's say you wanted to do two floats, or maybe you wanted 64-bit ints, right? So this point is generic such that any sort of type can be used for the two values. So you have the integer point, like I said, 5 and 10, and a floating point with the two values 1.0 and 4.0. Right. So this T means that any sort of type can be inserted into point, can be used as arguments, but for both x and y, they have to be that type T that's inserted, right? They have to be a consistent type. So like this says it won't work. X is 5, but y is 4.0. So this is an int, but this is a float, and that won't work because both of them have to be of type T, which could be anything, but must be consistent throughout inside the strut, inside the block or the body of the strut. When you think of hash maps, though, you could have the K type and the V type, and the K is the type of the key and the V is the type of the value that the key corresponds to, right? So you can define multiple different generics to go into one type, but you have to specify that explicitly. Yes, and this is how you do it, where you define it to be T and U, where X corresponds to T and Y corresponds to U, and at this point you can define either both of them to be an integer, both of them to be a float, or to have one of each, because you've explicitly defined the two to be different or to be independent of each other. They don't have to necessarily be different. They could still be the same type, but they're independent. And you can use generics for enums as well. So the option type, or the option enum, which we're familiar with, which is sort of Rust's implementation of null or nullable variables or traits or whatever. Not traits, variables or values. It can be some, so the option type has a generic, right? So it can either be nothing, in which case it doesn't really have a type. Nothing doesn't really have a type. Or it could be the actual something that would correspond to the variable being filled with something, whereas none would correspond to the variable being null. And the type of that variable would be passed in through T. Right, by using the option, or by using the generic option, we can express the abstract concept of having an optional value. And because option is generic, we can use this abstraction no matter what the type of the optional value is. Enums can use multiple generic types as well, so similar to how we defined it with multiple here, we can do the same thing with the result type that we used before in error handling, where if it's fine, it's T, where it's or use the OK type, or it's an error, in which there's an error type. Yeah. And I suppose similarly to functions, we can have methods be generics as well. So when we have a point, we can implement a method for it, in which it takes in. So how is it going to explain this? This is sort of interesting. It's a generic implementation for the generic point. I suppose you could have just another strut that is not a generic point, right? So this point t specifies that it's this that it cares about, and the implementation takes in a generic. Note that we have to declare t just after implementations, or impl, so we can use it to specify that we're implementing methods on the type point t. By declaring t as a generic type after impl, Rust can identify that the type in the angle brackets and point is a generic type rather than a concrete type. We could, for example, implement methods only on point f32 instances rather than on point t instances with any generic type. Here we use the concrete type f32, meaning we don't declare any types after impl. So here, that's what it's talking about. So here we could actually implement something that only operates on certain types of point, which had been defined as a generic, but here we're only operating on 32-bit floats. That's interesting. And because we're only operating on a single type, then impl doesn't need any sort of type declaration, because it applies to a strut with a particular concrete type for the generic type parameter t. And any other point that's not defined as f32, which doesn't have that as a type, won't have this function distance from origin, or it won't have the method distance from origin. Generic type parameters in a strut definition aren't always the same as those you use in that struct's method signatures. Alright, so for example, listing 1011 defines the method mixup on the point tu strut from listing 10.8. The method takes another point as a parameter, which might have different types from the self point we're calling mixup on. The method creates a new point instance with the x value from the self point of type v and the y value from the passed in point of type w. So here we have, okay, that makes sense. So this implementation is for, tu, which is here, for the point tu, and we're going to mix up taking in VW as its type, it's generic. Let's see how function. Is that how they define it? Yeah. So function, you need to also define the. Okay. Yeah, so this is the same as defining a function. Sorry. So it takes in a VW, and point is VW, and then it returns a point with TW. So T from the original point. Because its self is going to be of this type, and self is TU, and then we take some other point VW, which we defined elsewhere, that's not associated with self, and then returns the first one from self, which is T, and the second one from the other, which is W, and then it returns that, and then it returns the point. Cool. Yeah, so the implementation parameters are not necessarily the same as the function parameters within that implementation block. So the good news is that Rust implements generics in such a way that your code doesn't run any slower using generic types than it would with concrete types. Rust accomplishes this by performing monomorphization of the code that is using generics at compile time. Monomorphization is the process of turning generic code into specific code by filling in the concrete types that are used when compiled. So the compiler is going to make different versions of your function for all the different combinations of specific types that you put in for its generic types. So here, because you have sum of 5 and sum of 5.0, Rust compiles the code and performs monomorphization. During that process, the compiler reads the values that have been used in option T instances and identifies two kinds of option T. One is I32 and the other is F64. As such, it expands the generic definition of option T into option underscore I32 and option underscore F64, thereby replacing the generic definition with the specific ones. And so you would have two different versions of options like it has here. And because of that, we pay no runtime cost for using generics. When the code runs, it performs just as it would if we had duplicated each definition by hand. The process of monomorphization makes Rust generics extremely efficient at runtime. Cool. So now we'll learn about traits, defining shared behavior. A trait tells the Rust compiler about functionality a particular type has and can share with other types. We can use traits to define shared behavior in an abstract way. We can use trait bounds to specify that a generic type can be any type that has certain behavior. Traits are similar to a feature often called interfaces in other languages, although with some differences. Alright. A type's behavior consists of the methods we can call on that type. Different types share the same behavior if we can call the same methods on all of those types. Trait definitions are a way to group method signatures together to define a set of behaviors necessary to accomplish some purpose. For example, let's say we have multiple structs that hold various kinds and amounts of text. A news article struct that holds a news story filled in a particular location, and a tweet that can have at most 280 characters long with metadata that indicates whether it was a new tweet, a retweet, or a reply to another tweet. We want to make a media aggregator library that can display summaries of data that might be stored in either a news article or tweet instance. To do this, we need a summary from each type, and we need to request that summary by calling a summarize method on an instance. Here is going to be the public trait summary, and it has a function of summarize, which references itself or returns a string. And this definition of a summary trait expresses that behavior that we wanted. We declare a trait using the trait keyword and then the trait's name, which is summary in this case. Inside the curly brackets, we declare the method signatures that describe the behaviors of the types that implement this trait, which in this case is function summarize reference itself, returning a string. Yeah, so instead of providing an actual implementation of summarize, we just end it with a semicolon. And the type which wishes to implement this trait of being able to summarize something must define its own function of summarize that is specific to that type, such that it can have custom behavior. Because a summary of a tweet is going to be different than a summary of a news article. A trait can have multiple methods in its body. The method signatures are listed one per line, and each line ends in a semicolon. Yeah, one per line, so you just say, yeah, this trait could have as many functions as you want. It's one per line, you just separate them each with a semicolon. Alright, then this will be similar, like Russ said, to an, what was it, an interface? Yeah, an interface. Right, so a news article is going to implement summary for news article. So, okay, we have the struct news article, and then we wish to implement summary for news article. And then we define the summarize function to be this, like it said. It's just going to return the headline, author, and location. And then the summary for the tweet returns the username and the content. So the difference between this and a regular implementation is that we specify what we wish to implement summary for, or what we wish to implement the trait, or rather, which struct we wish to implement the trait for. And then we use each of the, how would I describe this? This is, what is it, method signature. So for each method signature, we have to actually implement it in this implementation, and we can omit the semicolon. And so now that both of them can call the summarize, or because both of them have implemented the summarize trait, they can, or the summary trait, they can now access the summary traits methods, which the only one there is summarize, and so you can now do it. And so the reason they are putting these pubs for everything is for the case when, let's say, pub is, I'm sorry, if news article were defined somewhere else, right, than lib, maybe it's in some other trait, some other crate, and the summary trait is defined in a separate crate from the other two structs that implement summary, and so you need to make the trait itself public so that other things outside of lib source file can implement it if that's what you wish. One restriction to note with trait implementations that we can implement a trait on a type only if either the trait or the type is local to our crate. For example, we can implement standard library traits like display on a custom type like tweet as part of our aggregator crates functionality because the type tweet is local to our aggregator crate. We can also implement summary on vect in our aggregator crate because the trait summary is local to our aggregator crate. But we cannot implement external traits on external types. For example, we cannot implement the display trait on vect within our aggregator crate because display and vect are defined in the standard library and are not local to our aggregator crate. This restriction is part of a property of programs called coherence, and more specifically, the Orphan Rule, so named because the parent type is not present. This rule ensures that other people's code cannot break your code and vice versa. Without the rule, two crates could implement the same trait for the same type, and Rust wouldn't know which implementation to use. Alright. So you must pretty much implement a trait on a type locally, pretty much, in the same file. And so if you wish to have default behavior, then you define it in the trait method signature here instead of just ending it with a semicolon. Oh, sorry, this is the method signature. And we can define default behavior for it instead of just leaving it as the signature. Okay. So because news article implements summary, and let's say it didn't have this implementation, right, we would have to specify an empty impl block with impl summary for news article and then open close curly braces. So let's pretend, I suppose, that we didn't have this function definition, and so we just had, we didn't even have the signature either. It's just open close for news article, and then it would just use the default behavior where it would just print out read more like we said here for summary, for the trait summary. And it's on a per method base that you can define, or yeah, whether you wish to define a default behavior or not. That's cool. However, this then must be defined by the implementation, even if they just want to use summarize instead of summarize author. It is not possible to call the default implementation from an overriding implementation of that same method. Good to know. Alright, so now that we know how to define and implement traits, we can explore how to use traits to define functions that accept many different types. Alright. Hmm. For example, in listing 1013, we implemented the summary trait on the news article and tweet types. We can define a notify function that calls the summarize method on its item parameter, which is of some type that implements the summary trait. So it's the item which implements the summary trait. To do this, we can use the impl trait syntax like this. So item can only accept something that implements the summary trait. Instead of a concrete type for the item parameter, we specify the impl keyword and the trait name. This parameter accepts any type that implements the specified trait. In the body of notify, we can call any methods on item that come from the summary trait, such as summarize. We can call notify and pass in any instance of news article or tweet. Code that calls the function with any other type, such as a string or an I32, will not compile because those types do not implement summary. The impl trait syntax works for straightforward cases, but is actually syntax sugar for a longer form, which is called a trait bound, and it looks like this, where this is equivalent to this, where it's a function notify of some generic t, I suppose some generic t that implements summary of an item whose type is a reference to t. T is of type summary, and item is of type reference to t, where t is some type which implements summary, and item is a type of reference to that t. We place trait bounds with the declaration of the generic type parameter after a colon and inside angle brackets. The impl trait syntax is convenient and makes for more concise code in simple cases. The trait bound syntax can express more complexity in other cases. For example, we can have two parameters that implement summary. Using the impl trait syntax looks like this. Item 1 is something that implements summary, and item 2 is a reference to something that implements summary as well. If we wanted this function to allow item 1 and item 2 to have different types, using impl trait would be appropriate, as long as both types implement summary. If we wanted to force both parameters to have the same type, that's only possible to express using a trait bound like this. So notify is the t summary, and item 1 is a reference to t, and item 2 is also a reference to t. Right, so the previous one using the impl trait syntax really only says that item 1 must implement summary and item 2 must implement summary. Any two types, let's say a tweet or a news article, could implement summary, but here it's saying notify accepts type T of summary, and that item 1 and item 2 must both be a reference to that type. And so T could either be news article or tweet, but item 1 and item 2 both reference whatever T is. And so if item 1 is a news article, then notify, this version notify, using trait bounds, is going to assume that T is a news article, and so it's going to enforce this other item 2 to also be a news article. Oh. And if we wish to specify more than one trait bound, we use plus. So if we want this item to implement both summary and display, then we have to specify that with a plus. And we can do that with the impl trait or with the trait bounds like this. Using too many trait bounds has its downsides. Yeah, it'll get complicated. Each generic has its own trait bound, so functions with multiple generic type parameters can contain lots of trait bound information between the function's name and its parameter list, making the function's signature hard to read. For this reason, Rust has alternate syntax for specifying trait bounds inside a where clause after the function signature. So instead of writing this long this long method signature or function signature, where the first argument, here you have the first argument is reference to T, second argument is reference to U, returns an I32 at the end, and T must implement display and clone, and U must implement clone and debug. And we can instead have it more succinct or concise by only specifying T and U at the beginning, where before we actually had the trait bounds specified along with them. Then we use this where block to specify what T and U actually are. And the opening curly bracket, which starts the block of the function, is specified after this where clause. So that way the parameter and return signatures are close together, and like it would be in a regular function without trait bounds. All right, let's see how stream is doing. Oh, it's doing beautifully. Cool. All right. We can also use the impl trait syntax in the return position to return a value of some type that implements a trait, as shown here. So the return type in this case implements a summary. So we're just going to return some tweet. But it doesn't have to be a concrete type, right? This could have been a news article, right? So long as whatever is returned is summarizable. Right, so closers and iterators create types that only the compiler knows, or types that are very long to specify. The impl trait syntax lets you concisely specify that a function returns some type that implements the iterator trait without needing to write out a very long type. However, you can only use impl trait if you're returning a single type. For example, this code that returns either a news article or a tweet with the return type specified as impl summary wouldn't work. Oh, so I was wrong. Wow. So we can you can write some function with this behavior, but this isn't the way to do it. If you're returning, so what you are returning has to implement summary. And really it could be either a news article or a tweet, but if anywhere you return something to implement summary, then elsewhere you have to return that same type. If there are multiple conditions in which you can return something. So now we're going to fix this bug that we had in 10.1, the previous section, where it said binary operation greater than cannot be applied to type T. And so now we're going to consider restricting type parameter T such that it implements partial ORed. So, alright, so now that you know how to specify the behavior you want to use using the generic type parameters bounds, let's return to listing 10.5 to fix the definition of the largest function that uses a generic type parameter. Last time we tried the code, we received this error, and in the body of largest, we wanted to compare two values of type T using the greater than operator. Because the operator is defined as a default method on the standard library trait standard compare partial ordered, we need to specify partial ORed in the trait bounds for T so that the largest function can work on slices of any type that we can compare that implement partial ORed. We don't need to bring partial ORed into scope because it's in the prelude. Change the signature of largest to look like this, where before it was just a plain old generic, and now we're specifying it as implementing partial ORed. We still receive errors. Alright. So it's saying that we cannot move out of type T, a non-copy slice. Cannot move out of here. Move occurs because list has type T, which does not implement the copy trait. So we have to probably put plus copy. Yeah, so when we made the largest function generic, it became possible for the list parameter to have types in it that don't implement the copy trait. Consequently, we wouldn't be able to move the value out of list of 0 and into the largest variable, resulting in this error. So now we're going to specify copy and partial ORed such that we can take whatever's in list and copy it into largest. Then we can return that separately from what's inside list. If we don't wish to restrict the largest function to the types that implement the copy trait, we could specify that T has the trait bound clone instead of copy. Then we can clone each value in the slice when we want the largest function to have ownership. Using the clone function means we're potentially making more heap allocations in the case of types that own heap data like string. And heap allocations can be slow if we're working with large amounts of data. Another way we can implement largest is for the function to return a reference to a T value in the slice. So instead of largest taking ownership of this item within a list, largest simply becomes a reference to that location in the list, and then you return a reference to T as opposed to the actual value itself. And because we're returning a reference, we never take ownership, and so we don't need clone or copy. And if we get stuck with errors having to do with lifetimes, we'll keep reading, because validating references with lifetime session coming up will explain. But lifetimes are not required to solve these challenges. All right. I'm gonna get some more water. I'll be right back. So, by using a trait bound with an input block that uses generic type parameters, we can implement methods conditionally for the types that implement the specified traits. Excuse me. For example, the type pair T in listing 1016 always implements the new function. But pair T only implements the comp display method if its inner type T implements the partial OR trait that enables comparison and the display trait that enables printing. So okay, let's see what's happening. So we just have this strut pair, and no matter what, so for any generic, we'll have a new method defined for it, and its default is just returning self of the two arguments. And then we'll have a different implementation such that if the type T implements display in partial ORed, and it reference pair T's, right? So it's for any T. If T implements these two traits, then we have this function defined for it such that we can display the comparison between the two what's the word for those? I suppose what are variables associated with structs called? I forget. But whether these two compared are bigger and you display which one it is. So, hold up. We can also conditionally implement a trait for any type that implements another trait. Implementations of a trait on any type that satisfies the trait bounds are called blanket implementations and are used extensively in the Rust standard library. For example, the standard library implements the toString trait on any type that implements the display trait. The input block in the standard library looks similar to this code. So it's an implementation on T, which implements trait. So we implement toString for T if it implements display. So because the standard library has this blanket implementation, we can call the toString method defined by the toString trait on any type that implements the display trait. For example, we can turn integers into their corresponding string values like this because integers implement display. And if you can display, then you can use this blanket implementation to call this function toString. Traits and trait bounds let us write code that uses generic type parameters to reduce duplication, but also to specify to the compiler that we want the generic type to have particular behavior. The compiler can then use the trait bound information to check that all the concrete types used with our code provide the correct behavior. In dynamically typed languages, we would get an error at runtime if we called a method on a type which didn't define the method. But Rust moves these errors to compile time, so we're forced to fix the problems before our code is even able to run. Additionally, we don't have to write code that checks for behavior at runtime because we've already checked at compile time. Doing so improves performance without having to give up the flexibility of generics. Another kind of generic that we've already been using is called lifetimes. Rather than ensuring that a type has the behavior we want, lifetimes ensure that references are valid as long as we need them to be. Let's look at how lifetimes do that. Alright. Alright. So here we're going to validate references with lifetimes. One detail we did not discuss in the references and borrowing section in chapter 4 is that every reference in Rust has a lifetime, which is the scope for which that reference is valid. Most of the time, lifetimes are implicit and inferred, just like most of the time types are inferred. We must annotate types when multiple types are possible. In a similar way, we must annotate lifetimes when the lifetimes of references could be related in a few different ways. Rust requires us to annotate the relationships using generic lifetime parameters to ensure the actual references used at runtime will definitely be valid. The concept of lifetimes is different from tools in other programming languages, or somewhat different from tools in other programming languages. Arguably, making lifetimes Rust's most distinctive feature. Although we won't cover lifetimes in their entirety in this chapter, we'll discuss common ways you might encounter lifetime syntax so you can become familiar with the concepts. Alright, so now we're going to learn how to prevent dangling references with lifetimes. The main aim of lifetimes is to prevent dangling references, which cause a program to reference data other than the data it's intended to reference. Here we have a program with an inner scope and an outer scope. And we just simply let R, and then within this inner scope, we let the R be a reference to X, which we define as 5. But then we come out of this inner scope, and then we try to print R. But this reference to X is invalid because it's you've now come out of scope. And so it's not going to compile. So this might seem that Rust allows null values, but really, if you were to try to use R without it being defined somewhere else, then you're going to get a compile time error. So Rust indeed does not allow null values. Yeah, so X has gone out of scope along with the reference to X and R, and so this cannot compile because we try to use it here. Alright, so the Rust compiler has a borrow checker that compares scopes to determine whether all borrows are valid. Listing 1018 shows the same code as listing 1017, but with annotations showing the lifetimes of the variables. Alright, so here we have A being defined, and then B being defined, and then it leaving, and then here is when A comes out of scope. Alright, so at compile time, Rust compares the size of these two lifetimes. So the lifetime of this and the lifetime of this. And sees that R has a lifetime of prime A, but that it refers to memory with a lifetime of prime B. The program is rejected because prime B is shorter than prime A. The subject of the reference does not live as long as the reference. So we fix the code by putting it back into the outer scope such that prime A and prime B both have the same lifetime. Here, X has the lifetime prime B, which in this case is larger than prime A. This means R can reference X because Rust knows that the reference in R will always be valid while X is valid. Alright, so we're going to write a function that returns the longer of two string slices. This function will take two string slices and return a string slice. After we've implemented the longest function, the code in listing 1020 should print the longest string as ABCD, because it's longer than XYZ. Right, so we want the function to take string slices, which are references, because we do not want the longest function to take ownership of its parameters. Right, I mean, we define string 1 as a string, but then we put it as a stir here, as a string slice. And if we try to implement it like this, apparently it won't compile. And if we take a stir slice and another stir slice and return a stir slice, and then we try to use them directly, it's not going to compile. I wonder why. Oh, because X and Y are defined inside function, maybe? No, they're parameters. This function's return type contains a borrowed value, but the signature does not say whether it is borrowed from X or Y. This function's return type contains a borrowed value, but the signature does not say whether it was borrowed from X or Y. So function does not know at compile time whether to borrow from X or to borrow from Y. And so it's going to suggest doing this, I suppose, to introduce lifetimes. Right, we don't know at compile time either, us with the bigger brains, if we're going to be borrowed from X or from Y, because, you know, these arguments could be anything. Yeah, we also don't know the concrete lifetimes of the references that would be passed in, so we can't look at the scopes as we did in listings 1018 and 1019 to determine whether the reference we return will always be valid. The borrow checker cannot return or cannot determine this either, because it doesn't know how the lifetimes of X and Y relate to the lifetime of the return value. To fix this error, we'll add generic lifetime parameters that define the relationship between the references so the borrow checker can perform its analysis. So, lifetime annotations don't change how long any of the references live. Just as functions can accept any type when the signature defines a generic type parameter, functions can accept references with any lifetime by specifying a generic lifetime parameter. Lifetime annotations describe the relationships of the lifetimes of multiple references to each other without affecting the lifetimes. So lifetime annotations have a slightly unusual syntax. The names of lifetime parameters must start with an apostrophe and are usually all lowercase and very short, like generic types. Most people use the name prime A. We place lifetime parameter annotations after the and of a reference, or the ampersand of a reference, using a space to separate the annotation from the reference's type. Here are some examples. So here we just have a reference to a 32-bit int. Here we have something, a reference with an explicit lifetime to a 32-bit int, and then here's the same thing, but it's immutable. So one lifetime annotation by itself does not have much meaning because the annotations are meant to tell Rust how generic lifetime parameters of multiple references relate to each other. For example, let's say we have a function with the parameter first that is a reference to an i32 with lifetime prime A. The function also has another parameter named second that is another reference to an i32 that also has the lifetime prime A. The lifetime annotations indicate that the references first and second must both live as long as that generic lifetime. Right, so first and second, if they're both annotated with the same annotation for a lifetime, then they're going to have the same lifetime. So they must both live as long as the other. So now let's examine lifetime annotations in the context of the longest function. As with generic type parameters, we need to declare generic lifetime parameters. As with generic type parameters, we need to declare generic lifetime parameters inside angle brackets between the function name and the parameter list, but we have to use prime or apostrophe in order to distinguish it from a generic type. The constraint we want to express in this signature is that all the references in the parameters and the return value must have the same lifetime. So x, y, and the return value must be the same lifetime. And when we do that, it should compile. The function signature now tells Rust that for some lifetime prime A, the function takes two parameters, both of which are string slices that live at least as long as lifetime prime A. Okay. The function signature also tells Rust that the string slice returned from the function will live at least as long as lifetime prime A. Okay. In practice, it means that the lifetime of the reference returned by the longest function is the same as the smaller of the lifetimes of the references passed in. Remember, when we specify the lifetime parameters in this function signature, we're not changing the lifetimes of any values passed in or returned. Rather, we're specifying that the borrow checker should reject any values that don't adhere to these constraints. Note that the longest function doesn't need to know exactly how long x and y will live, only that some scope can be substituted for prime A that will satisfy this signature. Right, and let's say x, the argument that ends up being passed in for x is defined with a shorter lifetime outside of the scope of function longest. It's defined with a shorter lifetime than y, or whatever's passed in as y. And so this longest function is saying whatever is passed out, whatever is returned, is going to be the smaller of these two, which will end up being x. Right, so this is what I'm going to be saying. This is what I was thinking of. So string 1 is of a greater lifetime than string 2 because string 2 is only defined in this block, whereas string 1 is defined in the whole main block. And so you're only going to be able to use the result of this longest, of whatever is returned from longest, within the shorter of the two lifetimes. And the lifetimes of these do not change from the longest function now suddenly having these lifetime annotations added to them. It's just that now we've explicitly said that of these two that are passed in, the resulting or the return of them, of the function that uses these two, is going to be the smallest of the two, such that it's enforcing that no dangling references will be made. Because if it were the longest of these two, then let's say string 2 was longer than string 1, right? And then we could put in string 2 and string 1, and then let's say string 2 happens to be the result, but if the lifetime ended up being the longest or the most expanded of the two strings, then we might reference it outside of the block in which string 2 was defined, and then we'd have a dangling reference. So we can't do that. It has to be the smallest of the two. And as such, we can only use result within this scope here. All right, once we try to use result outside of here, even though we define result in a larger scope, it won't compile because string 2 is the I suppose the weakest link in the chain, or at least the shortest lifetime of everything. As humans, we would know that this would end up being returned for result, but the compiler doesn't know that per se. So it'll throw an error. Alright, the way in which you need to specify lifetime parameters depends on what your function is doing. For example, if we change the implementation of the longest function to always return the first parameter rather than the longest string slice, we wouldn't need to specify a lifetime on the y parameter. The following code will compile. In this example, we've specified a lifetime parameter prime a for the parameter x in the return type, but not for the parameter y, because the lifetime of y does not have any relationship with the lifetime of x or the return value. Because we just return x, right? Y can be disregarded. Yeah, I didn't think this was going to compile. So when returning a reference from a function, the lifetime parameter for the return type needs to match the lifetime parameter for one of the parameters. If the reference returned does not refer to one of the parameters, it must refer to a value created within this function, which would be a dangling reference because the value will go out of scope at the end of the function. Consider this attempted implementation of the longest function that won't compile. So we tried to create a string inside the function that would return that result as a string, and then tried to annotate prime a as the lifetime. But it doesn't work because result is, its scope is within the function. It doesn't take any parameters. Yeah, the problem is that result goes out of scope and gets cleaned up at the end of the longest function. And we're also trying to return a reference to result from the function. There is no way we can specify lifetime parameters that would change the dangling reference, and Rust won't let us create a dangling reference. In this case, the best fix would be to return an owned data type rather than a reference, so the calling function is then responsible for cleaning up the value. Yeah, so you just return, let's say, just a regular plain old string, right? Just really long string, which can be owned, not referenced. Ultimately, lifetime syntax is about connecting the lifetimes of various parameters and return values of functions. Once they're connected, Rust has enough information to allow memory-safe operations and disallow operations that would create dangling pointers or otherwise violate memory safety. So now we'll move on to structs. Alright, so far, we've only defined structs to hold own types. It's possible for structs to hold references, but in that case, we would need to add a lifetime annotation on every reference in the struct's definition. Here's a struct called important excerpt, which holds a reference to a stir or string slice with the lifetime annotated here. As with generic data types, we declare the name of the generic lifetime parameter inside angle brackets, blah, blah, blah. This annotation means an instance of important excerpt cannot outlive the reference it holds in its part field. Oh, makes sense. Okay. So, pretty much this I of type important excerpt cannot be used outside of which it's cleaned up. All right. So we had a function before that compiled without lifetime annotations. So what happens? So the reason this function compiles without lifetime annotations is historical. In early versions, pre 1.0 of Rust, this code wouldn't have compiled because every reference needed an explicit lifetime. At that time, the function signature would have been written like this. The first word, prime A of S of a reference to prime A stir, returns a reference to prime A stir. After writing a lot of Rust code, the Rust team found that Rust programmers were entering the same lifetime annotations over and over in particular situations. These situations were predictable and followed a few deterministic patterns. The developers programmed these patterns into the compiler's code so the borrow checker could infer the lifetimes in these situations and would not need explicit annotations. This piece of Rust history is relevant because it's possible that more deterministic patterns will emerge and be added to the compiler. In the future, even fewer lifetime annotations might be required. The patterns programmed into Rust's analysis of references are called the lifetime elision rules. These are not rules for programmers to follow. They are a set of particular cases the compiler will consider, and if your code fits these cases, you don't need to write the lifetimes explicitly. The elision rules do not provide full inference. It for us deterministically applies the rules, but there is still ambiguity as to what lifetimes the references have. The compiler will not guess what the lifetime of the remaining references should be. In this case, instead of guessing, the compiler will give you an error that you can resolve by adding the lifetime annotations. Lifetimes on function or method parameters are called input lifetimes, and lifetimes on return values are called output lifetimes. There are three rules if they're not explicit. The first applies to input lifetimes, and the second and third rules apply to output lifetimes. If the compiler gets to the end of these rules and it still cannot figure out some of these lifetimes, you'll get an error. They apply to function definitions as well as impl blocks or implementation blocks. The first rule is that each parameter that is a reference gets its own lifetime parameter. In other words, a function with one parameter gets one lifetime parameter. So a reference to int32 is going to have its own lifetime parameter separate from, let's say, another reference to another int32, which is going to have its own. Second rule is that if there is exactly one input lifetime parameter, that lifetime is assigned to all output lifetime parameters. So here you only have prime A, and it's going to be assigned as the output. There are multiple input lifetime parameters, but one of them is a reference to the self or a reference to immutable self. Because this is a method, the lifetime of self is assigned to all output lifetime parameters. This third rule makes the methods much nicer to read and write because fewer symbols are necessary. And now we're going to pretend that we're the compiler. So we'll apply the first of these rules here, where we just stick in prime A for each reference that we find, and then because there's only one prime A, we stick it on the output. And now we have the lifetimes that we expected to have in this function from chapter 4. But here we have some different rules. So we have X and Y are both references, so they're going to have their own lifetimes, but it can't figure out what the output is because they only infer what this will be if you had exactly one, or if it was reference to self or mutable self. And then we get an error because the compiler just doesn't put it in. Alright. When we implement methods on a struct with lifetimes, we use the same syntax as that of generic type parameters shown in listing 1011. Where we declare and use the lifetime parameters depends on whether they're related to the struct fields or the method parameters and return values. Lifetime names for struct fields always need to be declared after the impl keyword and then used after the struct's name because those lifetimes are part of the struct's type. In method signatures inside the impl block, references might be tied to the lifetime of references in the struct's fields, or they might be independent. In addition, the lifetime elision rules often make it so that lifetime annotations are not necessary in method signatures. Now look at some examples. So I'm going to implement with the lifetime of prime A, import an excerpt with prime A, and then we're going to define a method called level that takes a reference to self and then returns i32 of 3. And using the elision rules, reference is going to have its own lifetime, and because it's a reference to self, you're going to use that lifetime for the output. And does it assume it's going to be prime A? here's something else. So announcer return part, so we have a reference to self. Announcement is a reference to stir, and we return a reference to stir. And so there are two input lifetimes, this guy and this guy, and then we're going to print something, which is this, and then we're going to return self.part, and that we defined all the way over here, which has a lifetime of prime A, and it's identical with the lifetime of the struct itself. So return self.part, and part has the same lifetime as self, right, which we saw over there. It has the lifetime of prime A, and because a reference to stir automatically, or this output lifetime is going to automatically be the same as the lifetime of self, then you don't need reference annotations. Oh, now there's a static lifetime, this guy. So this means that this reference can live for the entire duration of the program. All string literals have the static lifetime, which we can annotate as follows. The text of this string is stored directly in the program's binary, which is always available. Therefore, the lifetime of all string literals is static. You might see suggestions to use the static lifetime in error messages, but before specifying static as the lifetime for a reference, think about whether the reference you have actually lives the entire lifetime of your program or not. You might consider whether you want it to live that long, even if it could. Most of the time, the problem results from attempting to create a dangling reference or a mismatch of the available lifetimes. In such cases, the solution is fixing those problems, not specifying the static lifetime. Alright, let's briefly look at the syntax of specifying generic type parameters, trait bounds, and lifetimes all in one function. So you have to specify them separately. So you specify the lifetime and the generic trait separately. And in the method signature, the function signature, that's where you define the lifetime. Annual is just another, or announcement is just another argument. And it returns a reference to stir with the same lifetime as these two. We did not annotate announcements lifetime, and we specify the trait bound for T. It must implement display, and this is the function body where we print announcement. And because announcement doesn't have anything to do with what we're ending up returning, what we're going to end up returning, that's why we didn't need to annotate it with any lifetime. It's completely irrelevant to what's being returned. And then we have a function that we're familiar with here. Because lifetimes are a type of generic, the declarations of the lifetime parameter prime A and the generic type parameter T go in the same list inside the angle brackets after the function name. Right. Oh, this is important. But now it has an extra parameter named an of the generic type T, which can implement display, is the only one which implements display, by the way, because it must be printed. This extra parameter will be printed before the function compares, and that is why the display trait bound is necessary. Alright, I will give them that they've covered a lot in this chapter. So now that I know about generic type parameters, traits, and trait bounds, and generic lifetime parameters, and so on, I'm I'm ready to write code without repetition that works in many different situations. Generic type parameters let you apply the code to different types. Traits and trait bounds ensure that even though the types are generic, they'll have the behavior the code needs. You learned how to use lifetime annotations to ensure that this flexible code won't have any dangling references. And all of this analysis happens at compile time, which does not affect any sort of runtime performance. Believe it or not, there is much more to learn on the topics we discussed in this chapter. Chapter 17 discusses trait objects, which are yet another way to use traits. There are also more complex scenarios involving lifetime annotations that you will only need in very advanced scenarios. For those, you should just read the Rust reference. But next, you'll learn how to write tests in Rust so you can make sure your code is working the way it should. Bam! Alright. So this is going to be our penultimate chapter before we lessen the tempo on reading the book. I think once we are done with chapter 12, we'll start trying to do our own stuff, and we'll interspersed with continuing to read the book, because of course it's pretty valuable. But yeah, I'm at the moment interested in non-smooth dynamical systems. So looking at Psychonos, which is it's open source scientific software primarily targeted at modeling and simulating non-smooth dynamical systems. Yeah, it's useful for like switching for switching electronics like power converters, rectifiers, blah blah blah. And I would like to, I don't think there are any crates in Rust that really implement any sort of non-smooth dynamical systems. So I'm gonna have to research that. At least I didn't look very hard for Rust, so I'm going to have to research that some more. But if not, that's where I want, I think, to begin my I suppose projects, like personal projects, just to implement something like that, because I think it's going to be useful if we wish to end up making some sort of simulator. Because not only is it useful for things like event-driven, which to be honest, event-driven simulation is not very efficient. People tend to use one-step algorithms versus event-driven. I've gotta research more, but regardless, it's good for that, and also for modeling switching and any sort of, and I think it's a better way to model stiff nonlinear relations like in diodes and transistors and stuff. So especially when you just wish to deal with ideal characteristics of them, or if you want to implement, let's say, piecewise approximations of them, piecewise continuous, that is. So I'm excited to learn about, well, first to learn about non-smooth dynamic systems, and also to implement some functionality in Rust, assuming that nothing's already been made for it. I know that you could just, I suppose, create Rust bindings for the C API from Sykonos, but I don't know. I'm here to learn Rust, right? Not to just be making these bindings. And I'm also here to learn about those concepts because eventually I do want to apply it to web GPU, actually. So, yeah. And I'm not sure if just how easy it would be to use those C API bindings for something like a GPU architecture, right? So it might just end up being easier to just create it from scratch, especially on such a new GPU API. So with all that said, it's time to go because my throat is getting a little hoarse. So I'm gonna end the stream. I was reading a lot more from the text. I hope that was helpful than before, where it's me sort of just reading a little too silently, I think. So I hope that is appreciated. Well, anyway, I'll see y'all later. Goodbye.